He's a senior software engineer at CSCS, and he's going to talk to us about operating Alps at scale. So, all yours.
Okay. So, thank you, everyone. My name is Massimo Benini. I'm leading this group at CSCS called DWDI, Data Warehouse and Data Intelligence. And the mandate of this group is about providing observability at all levels for everything that's happening in our data center, from the managers to take a wiser decision, to our colleagues, sysadmin, to understand when there are problems, to users to understand how they're using the machine, to understand how much credits they have left on that. Today, I'd like to bring you to 3 interconnected threads that at the end define how we operate Alps, our flagship supercomputing. It's a Cray EX supercomputing. And these threads are, I will talk about this modern observability platform that we built. Then I'd like to introduce you to OpenCHAMI, this new system management layer that we are going to use in the next phase. And then I will talk about semantic digital twin of our data center. Let's start. So a bit of a context. These are the specs of Alps. This nice picture from the machine room. It's a mixture of different hardware, but you can see the main batch of hardware is composed with NVIDIA Grace-Hopper nodes, more than 10,000. It runs a slingshot network, and okay, he has a very higher power envelope compared to the previous one, because running Grace-Hopper chips at that scale, it consumes a lot of power. As you can see in the picture, on top of Alps, you can see different platforms like climate and weather, HPC User Lab, machine learning for the Swiss AI initiative. And what makes Alps particularly interesting from an operational standpoint, it's its versatility. So it's not just a static batch compute cluster, but as you can see, it serves multiple communities and has this concept of vCluster and vServices that allows some dynamicity in the way we operate this platform. So what we are able to do with Alps is to dynamically partition our infrastructure into what we call vCluster. V stands for versatile cluster. And in this way, what we can do is to increase or decrease the size of a vCluster in a very short amount of time. On top of the vCluster, we have the concept of the vService, that are services that we build upon this vCluster, and that allow us to really not having, for instance, the same user environment for the whole machine. But we can really silo it and tailor specific vCluster for different communities. Exactly. So it's a three-tier abstraction layer. So infrastructure as a code, where we can define, okay, this node belongs to this vCluster from now on. A service manager, which is a layer where we operate the vCluster. So here there are services that, for instance, take care of node vetting, checking on the nodes if something happened. And then on top, we have the user environment, where we really characterize the application layer on top of this vCluster. And that's the context that, in short, what is the difference between a traditional HPC data center and Alps. With Alps, basically what we try to achieve is to merge traditional HPC cluster with cloud initiative, basically, cloud stuff. So exactly, but okay, so now we have this Alps new machine. How does this basically interfere with the observability system that we would like to have for this new machine? And it's all about challenging. So the first challenge, sorry, I didn't move. Is that the new machine introduced the first challenge was the scale. Because when Alps was online, the volume of the telemetry data that we were now collecting from like hardware sensors, Slurm, Slingshot, CDUs, increased by almost 2 orders of magnitude compared to what we had before. The second hardware is heterogeneity, because as you can see, we have different architecture from AMD to different kind of NVIDIA, so multi-core and GPUs, and handling different kind of hardware. So that means that they have different telemetry interfaces, they collect different metrics, the same field have different names, the sampling rate is different, so we need to build a unified view across all these different nodes. And third, which is connected to this vCluster technology, so basically we need to integrate what we already have in our observability platform to this vendor-provided HPE Cray System Management called CSM stack that was shipped with the machine, and that we had to use it. Let's move. So this is to give you a sense of what we actually collect, and to walk you through our data taxonomy. So we mainly collect telemetry data, so a lot of time series database from node power, which was a really hot topic due to the fact that we are using NVIDIA Grace-Hopper, traditional system metrics, cabinet power, slingshot data, CDUs power, inlet and outlet water pressure, and then of course we need to always and constantly collect Slurm accounting data, storage data, because we also give a quote to our user. Recently, we are providing also inference service for the Swiss for the AI, all the AI workflow. So we have to also collect how many tokens the user are using, and so on. And also security data. Our CM is based on audit bit, reframe data, because every time we deploy a new vCluster, and often there is this reframe layer which run application test, and tracks the performance of the test. So we need to ensure that every time we do some updates in the software stack, the performance improve, or at least stay the same, not decrease. And also we collect what is called application performance metrics. So basically people that want to instrument their code and want to see these logs in a observability platform. How is done, what we consider an observability cluster. So I've reported a few tools that are more or less equivalent for each rectangle. So, but basically it's all about some data collector that are as light as possible, and sometimes they use a push or a pull model, but what they do, they basically collect the metrics, and then everything is forwarded to a message broker. We use Kafka. It's a streaming queue system. It uses a producer and consumer model the good things about that is that you can really fan out the data using this model, because you can attach several consumers to a topic, so and that's really useful. Then in the middle we have some data aggregator and processing, where sometimes we need to enrich the data with other information, especially in the case of the V-cluster. Every time we get a matrix, a telemetry data, we need to inject, for instance, this node, this need belongs to, in this moment, belongs to this V-cluster, because tomorrow maybe it belongs to another V-cluster. Then we store this data depending on their nature. So we recently now, we moved towards Victoria metrics for metrics because of their performance, and logs to Elasticsearch. But we also have a lot of databases when we build APIs on top of that. And then for the visualization part, we are consolidating basically Grafana, but also we have API on top of that, also Kibana or Open Dashboard, we use both. Then I'd like to mention Airflow, which is an orchestration workflow engine, because sometimes we need to run transformation on the data, and we use that. It's basically a kind of like a cron style that you can instrument DAGs and run transformation and sync the data to wherever you want. Okay, so with Alps, this system called SMA, so Cray System Management, is shipped with the system monitoring application, which is basically what is provided by HPE. And as you can see, it resembles more or less exactly what we were doing for our observability platform. So, and it really overlaps what we are doing. So what we decided to do was to so our strategy was to treat CSM SMA as an upstream producer for our observability platform. So we install a battery of Fluent bits, which are basically forwarding all the Kafka topic already collected in SMA. We were not using the visualization part, that even if it was already there, but we wanted to consolidate our own visualization, and that's what's with this architecture, we were able to have a unified observability platform that works together with SMA. We use Grafana we're consolidating Grafana for all the main visualization for CSCS employee. Actually, we have two instances of Grafana. One is public, it's called observe.cscs.ch. We use Airflow to tag some dashboard in our internal Grafana in order to be, and when we tag this dashboard, there's an Airflow that automatically push data into the Observe for dashboard that we want to share externally without any authentication, basically. And then we recently are exploring dashboard as a service, as a codes, which is a new feature that exploit this Git sync. So basically, it's really cool. You can define dashboard in a Git repository, and it's automatically push and pull in your Grafana instance. We also are able to have this multi-tenancy paradigm due to the fact that there are different communities that they belong to different vCluster. Thanks to all the automation that we do and this GitOps approach that we have, we are able to spawn a small observability cluster per customer. And this is thanks to basically how we manage our platform, which we use these three components. One is Terraform, that provide the infrastructure in a declarative and idempotent ways. Then we use Harvester that provide the hyperconverged layer. So is essentially basically Kubernetes native virtualization using KubeVirt. And then we use Rancher on top of that to provide a unified management plane for all of our Kubernetes cluster and provide role-based access control, cluster provisioning, an easy way to upgrade all the Kubernetes cluster. This is how it works, but I need to speed up a bit. One thing I'm a bit proud of is this new GitOps approach. So all of our infrastructure is defined in a Git repository, and then there is this tool called Argo CD, which is constantly looking at your infrastructure as a code in the Git repository, and basically is the glue between your what's written in the GitOps and what's deployed in your vCluster, in your cluster. So you can you do a push, a commit, and then everything is automatically reproduced in your Kubernetes cluster. Due to the amount of data that we have been through a data catalog and classification process, and this was at some point really helpful to also understand all the amount of data that we were collecting. And then let me talk about OpenCHAMI. So why OpenCHAMI? So the main driving reason is because CSM is going to be discontinued. So the way from HPE, the way we manage the system management is going to be discontinued. And now there is this OpenCHAMI that stands for Open Composable HPC and AI Management Infrastructure. It's a consortium-driven set of composable software to enable sysadmin to secure and quickly provision and manage HPC and AI system at any scale. So this was the official definition. So in practice, it's a lightweight modular replacement for what was HPE CSM system management stack, and it's community-driven. You can see the actors behind. There are Los Alamos, NERC, so two of the biggest DOE US labs. There is us, CSCS, University of Bristol, and also both Dell and HPC are contributing to this project. What is and what is not? So it's a suite of microservices and associated tool that make up a site and vendor-agnostic HPC system management tool. It's not a clone of HPE CSM. It's not a battery-included HPC management system. So a lot of things that were in the CSM are not here. So it's a much simpler system with hopefully lower maintenance cost than CSM. And exactly, to reduce the aim is to reduce the overall production downtime. Some of the microservices are really forked from CSM. Other are not. A few design principles. So what's the philosophy behind the OpenCHAMI? So it's a system. I think it's built with having in mind that the person that has to run the system. So every design choice prioritize reducing unplanned maintenance activity and ensuring that the system means have full visibility and control over the system. It's there's a quote that say the easiest way to manage complexity is to remove it. So it's designed to be as simple as possible. Yeah, basically say use complexity only when it's useful to the sysadmins. These are more or less the components, the core components, which the SMD, the state management daemon, which is a kind of compute node inventory, the boot script service that generate the script that you can boot through iPXE compute node. I think it revolves around I don't remember the tool right now. And then you have Magellan, which is the service that discover and manage hardware using Redfish, the Redfish endpoints. And then you have extra components like secret management, Vault, image repository, but these are not part of OpenCHAMI. So that allows every data center to integrate with its own ecosystem. This is more or less what the architecture. I think it's interesting here the fact that there are different ways to deploy it through a Docker Compose, Podman Quadlets, which are basically containers that are managed like systemd. So you can run systemctl, and I think it's a cool alternative. Helm chart if you're running on top of Kubernetes or customized, which I never try. And that's the roadmap that we have at CSCM about the adoption of OpenCHAMI. 26 Q2, so we are working on monitoring alerting integration, because the big point is that if tomorrow we're gonna use OpenCHAMI in favor of HPE CSM, we are gonna lose a lot of data and metrics. So this is a kind of opportunity for us to redefine what we want to collect and redefine the monitoring and the alerting, what we want to have in OpenCHAMI. It's an open consortium, so I encourage you to contribute if you want to contribute. It's an open source project. There are Slack and everything. I have just a few minutes to talk about another initiative that we are working in my group. So it's about having a semantic digital twin. This is about to answer a problem that even with the observability platform that we have, there's still a problem that there's a lack of holistic overview of all the center of all of their assets. Sometimes we use different tools. For instance, we use OpenDCM to know about the hardware management that is in our machine room. We use Netbox for things that are related to network, satellite, for managing the images, and this lack of traceability, having these tool functions as isolated silos. So our solution, it's a bit provocative, it's leveraging neuroscientific tool to manage the next generation of software-defined supercomputing. This is why, because we took inspiration from a project called Knowledge Graph, built from the Human Brain project, and associated to CSCS since 2024. We've been lucky enough to get this some personnel that previously were working, are currently also now working on this project. It has in mind this FAIR principle, so the data should be always findable, accessible, interoperable, and reusable. And basically our approach was to, we didn't want to replace this existing tool. This domains tool needs to continue to exist, but we would like to build an aggregation layer on top of that. So data from all the sources is extracted and mapped to a common metadata structure and stored in a graph database. That's how we call the tool. It's called Marmot Graph, Management Application for Rich Metadata Objects in a Graph. It was hard to find an acronym like that, but we wanted that sound a bit Swiss, so we want an animal that lives in the mountain. Yeah, and here there's the site, you can have a look. Basically, it's more just a graph database. So the graph database is the main layer, but you have an explore tool where you can go through the graph, you can reach the data, validate the data, consume, automatize, organize, and everything. So this is a bit of architecture. Yeah, let's talk about the model has been built to a bottom-up approach. So we went through all the various departments and sit down with them, trying to, for instance, to the network department, understand how they would model their piece of the data center from their point of view. And basically, we build entities and relationship between entities. And then in order to create a shared model, a model that can be shared to any data center. And then of course, I had to apply some of customization for CSCS because we have the concept of vCluster, vService. Also, we are organized in a matrix organization. We have to take into account our custom things. So this is how the model looks like. Just to compare, the eBrain has 4.4 million entities. CSCS within 1 year work has 240,000 entities, which are the nodes on the graph that we have mapped. But yeah, let me just to maybe you didn't grasp how we use this tool in our daily work. Maybe let me jump to this one, which was a real use case. So in August 26, I don't know if you heard about the Bitnami case. So suddenly the Bitnami, so it was handling Docker images. So from day to night, they decided to move all their images, Docker images, to migrate to a legacy repository. And that was basically pose a critical operational risk. So any Kubernetes pod restarting or rescaling would have failed because in the image pool, basically they changed the repository. So before, for us to understand who was using, how to have a plan, a mitigation plan, that was a mess. With the Marmot graph, with a simple query that traversed all the graph, in one query we were able to provide a plan, to a mitigation plan, and understand who was the impact of this. And let me go to the last slide, because I haven't spoke about AI, so I need to at least have one AI slide. And yeah, these graphs are good to interact with LLMs. And what we'd like to do with this knowledge graph is to have the ability, because at the moment doing a query, it's a bit of complex. You need to understand how the graph is built. We would like to use the graph like a RAG in order to, with a natural language, ask to an LLM and use this Marmot graph as a graph RAG and exactly talk to asking question in a natural language way. And this is what we are actually working and improving. We are using this hybrid graph RAG because yeah, it's a bit complex. So yeah, I hope I wasn't too fast. I had to cover 3 topics, and yeah, that was the end of the presentation. Thanks.
Okay, we have time for questions.
Hi, Massimo. Thank you very much for the presentation. I do have a question about the last topic. And obviously, your graph is only as useful as complete it is, right? How much automation you have to populate the graph?
A lot.
Especially regarding the example that you set up about the Kubernetes pods. And how much you're doing manually?
It's everything it's automated as possible, you know. Yeah, because automation is the key to have updated information in the graph, otherwise it doesn't work. There are very small use cases where maybe we use we have to create a table or inject, or there's the possibility to inject manual data in the graph. That's possible, but I don't know, we use manual entities only when we cannot do some automation on them. We cannot inject automation on that. Also, Marmot Graph is open source, so have a look if you're interested.
Any other questions? No. If not, we are just in time to welcome Jordi to the stage.